So today, we're going to pull back the curtain on the transistor, the microscopic giant that really powers our entire digital world.
And to really get our heads around this, let's start with a question you can probably picture. Imagine you're at a concert. The singer whispers into a microphone, and a split second later, that tiny sound absolutely fills an entire stadium. How in the world is that possible? How does such a small input create such a massive output?
Well, the answer lies in a process called amplification. It's all about taking a small signal and making it much, much bigger. And the device that absolutely perfected this is what we're here to talk about.
Say hello to the transistor. At its heart, it's a tiny device that can either amplify or switch electronic signals. But here's what's really cool. The name itself is a clue. It's not just some random techie term, it's a mashup of transfer resistor. And that perfectly describes its job, transferring a current across a part of the circuit that can change its resistance. Seriously, keep that idea in your back pocket, because it's going to be super important.
Okay, so its name gives us a hint about its job, but what is this thing really? Like, if we could shrink ourselves down, Ant-Man style, and look inside, what would we actually see?
At its core, a transistor is basically a three-layer sandwich made of a special material called a semiconductor. Now, there are a couple of families of them, but the most common one, and the one we're going to focus on, is called an NPN transistor. You can just think of it as two N layers of material for the bread and a super thin P layer for the filling. The whole point of this weird sandwich is to perfectly control the flow of electrons.
And each of those three layers has a specific name and a job. First up, you've got the emitter. Think of it as the source, where all the electrons start their journey. Then on the other side, you have the collector, which is the destination. And squished in between them is the most critical part of all, the base. The base is this incredibly thin layer that acts like a gate, controlling the huge flow of electrons that wants to get from the emitter to the collector.
So, we have our three-layer sandwich. But here's the catch. On its own, it doesn't really do anything. To unlock its power, we need to add a secret ingredient, a process called biasing. This is basically how we flip the on switch. In its natural, default state, when it's just sitting there, the transistor is off. At the boundaries between the layers, these natural energy barriers form. You can picture them as potential hills that the electrons just don't have enough energy to climb over. So, no current flows. The gate is completely closed. But now, this is where the magic happens. By applying some specific voltages from the outside, that's the biasing part, we can literally change the height of those hills. We can strategically shrink one hill down to almost nothing, making it easy for electrons to cross, while at the same time making the other hill even bigger, which creates this powerful attraction. And by doing that, we open the gate and create a clear path for the current. And it all comes down to two golden rules. To get this thing to amplify, that first junction, the one between the emitter and the base, has to be forward biased. All that means is we give it a little voltage nudge to flatten that first hill, letting electrons just hop right over into the base. And at the exact same time, the second junction, between the base and the collector, has to be reverse biased. This means we hit it with a much stronger voltage that creates a huge pull, basically yanking those electrons across toward the collector. So you have one small push and one big pull. That is the secret.
All right, we've biased it, we've turned it on, we've created the path. So now for the payoff. Let's see how this whole setup lets a tiny, tiny signal control a massive one. Remember that super thin base layer? Well, it acts as the ultimate gatekeeper. By sending a teeny tiny little current into that base, we're basically handing it the key to open the main floodgate. This small base current, which we call IB, is what allows a much, much, much larger current to rush from the emitter all the way to the collector. And when I say a tiny current controls a massive one, I'm not kidding. The scale is just incredible. I mean, look at this. The base current, our little key, is measured in microamps. That's millionths of an amp. But the collector current it unleashes, that's measured in milliamps, thousandths of an amp. We're talking 1,000 times bigger. It's literally like a whisper controlling a shout. And it all boils down to a really simple, kind of beautiful piece of physics. The total current flowing out of the emitter is just the sum of that big collector current and the tiny little base current that was controlling it all. This simple formula, IE equals IC plus IB, well, that's it. That's the mathematical proof of amplification right there.
So, how do engineers actually know how a specific transistor is going to behave? They don't just guess, no way. They use something that's basically a performance report for the transistor, a set of graphs they call characteristic curves.
And this one is the most important one, the output characteristic curve. Think of it like a cheat sheet. It tells you exactly how much output current you're going to get for a certain output voltage, all depending on that tiny little input current you're feeding the base. It's the transistor's whole resume, right there on one chart.
And if you look at that curve, you'll see it reveals 3 different ways the transistor can operate. You've got the cutoff region, which is just fully off, and the saturation region, which is fully on. Those two are great for acting like a simple switch. But the real magic happens in that big zone right in the middle, the active region. That is where amplification lives.
So what makes the active regions so special? Well, in this zone, the output current becomes a direct, proportional, and much larger copy of the input current. If your tiny input signal wiggles up and down, the huge output signal wiggles up and down in the exact same pattern, just way bigger. That's what true high-fidelity amplification is all about.
So let's just do a quick recap. A transistor's name, transfer resistor, tells you exactly what it does. It's a 3-layer sandwich: emitter, base, and collector. The secret to making it work is biasing. A little forward push on the first junction, a big reverse pull on the second. And the whole point is that a tiny base current ends up controlling a massive collector current. And that, my friends, is amplification.
So there you have it. The transistor is just this beautiful, elegant example of how a very small, very precise input can control a massive output. Now that you get the basic idea, I'll just leave you with this final thought. Where else in life, completely outside of electronics, do you see that exact same powerful principle at play? Think about it.